Yes, you could put them full screen. Thank you.
Yeah, okay. So
Worked.
I'm sorry that I changed the title a little bit relaxed. So yeah, I'm going to talk about first robotics experiment and something related to the subjective phenomenology of subjective experience. So okay, so my talk today is the first is that an overview of predict coding, active inference. That is under the free energy principle. That's I have worked like 20 years. So then we're going to introduce particular recurrent type neural network and variational recurrent network. That is a tool to implement the idea of predict coding active inference, and show some robotic experiments using this model. And then I'm going to show some kind of social interaction. That's a robot-robot interaction, human-robot interaction, and then try to say something about the primary intersubjectivity, and the goal direct planning based on active inference, the online planning for the future while reflecting the past. That is a prediction and post-prediction things. And the emergence of a Prefrontal-Like executive control. So then, yeah, I like to finally, as I said, it's a possible correspondences to the phenomenology of the subjective experience. So that is today's scenario. Okay, so and then if you got interested in my talk a little, and then this advertisement, it's 5 years ago, I wrote a book about exploring robotic minds. So if you're interested in, please look at this one. So, okay. First, I like to start with a brief introduction about the predict coding, active inference. So predict coding is a kind of a theory for the perception. So that a lot of people discussed already. So, but the idea is that so we have a top-down prediction about sensation. Then we try to minimize the error between the top-down sensation, sensory prediction, and its bottom-up outcome reality by influencing the latent variables. So that's the internal state of the subject. So that is a theory, kind of a theory for the perception. And the active inference is for the theory for action generation. So this is a recent one, especially discussed by the Carl Friston. So that is the idea is that, again, this is going to minimizing the error, prediction error. But this time, we're going to, by changing the sensory inputs, by adequately acting on the environment. So that is kind of how it's kind of determine how to act in order to minimize prediction error in the sensation. But these two, the one for the perception, one for the action generation, are not separated process as the action and the preparation, perception make a loop through the environment. So now I'm going to show you a little bit the picture, illustrated picture, how it looks like. And also that is, I have worked on a relatively long time. So then we have worked like a kind of a hierarchical recurrent neural network, and especially the higher level, maybe Prefrontal-Like things, and this is sensation, sensory peripheral, but the higher level is operated in much far slower. And then these peripheral part is much faster. We may consider like a maybe multi-modality of sensation, like this path is going to be the proprioception for something like a posture of a body and something more movement related. And this is a vision exteroception thing. So then idea is that we have kind of a top-down intention and associating with the acting, so intending to act to the environment with some sort of prediction about the vision and the proprioception. So in this case, then proprioception is I'm going to move my hand in this way or something like that. That is something in case of a robot, that's kind of a predicting next target joint angle. And that's fed into the PID controller, motor torque generated, actually acting on the environment. And then we have a state change in the environment. Then we're going to have a proprioception and vision things come. So then we have a kind of a prediction and the reality comes, and then we're gonna have some kind of error. And the error might be, so this proprioception error is further is put into the PID controller and regulating motor updating. And but further, the more error for the both proprioception and the vision is bottom up, through the hierarchy, and then try to minimize this error by updating the intention. So that is, I say prior later. So it's going to be, so this is kind of a looping. So the idea is something like, so the intention update. So, but the idea is that we have the first part is it's a changing internal state by the bottom-up signal. So that is a perception part. And the other things is changing the world by the active inference. So then we have a lot of interaction. So that is while I'm acting on the environment, but still it's kind of you see the reality through the inference, and your mind is going to change. So that is which I'm going to more change, and that depends on the way of interaction. Then we have to look at what kind of interaction goes on. So that is something very essential part of the embodied cognition, I think. So, however, so in technically, this model is deterministic recurrent neural network model. So, and then no probabilistic treatment. So, and however, yeah, I have worked on this idea like maybe pseudo probability by self-organizing deterministic chaos inside, but still, so then I come to the question that so how we can resolve the gap between the deterministic formulation and the probabilistic one, and then are there any ways to bridge the gap between the two, that is deterministic and the probabilistic? And also, I'm very much interested in the origin of the phenomenology of the probabilistic. So then I come to the free energy minimization by Carl Friston. That's I gave talk his laboratory more than 12 years ago, and then we talked, and I got inspired very much by Carl Friston that time. So then I started to change this model to the variational free variational schema. So that is toward free energy minimization. So I worked on. So then maybe I'm going to show you some brief explanation of the free energy in terms of generative model and the inference model. So the idea is that this is quite a standard picture. So that is we have these latent variable, and then we have the kind of prior distribution of this one. And this is a theta as a parameter that we have likelihood. And then we're going to have a kind of expectation of the observation. And the reality comes, this is a real observation, and then we have the error. And then we want to minimizing this error by approximating the posterior. So from the and then it is known that if we make this scale divergence between the prior and the posterior minimizing, then we will get this one is going to approach to the approximated one going to be the true posterior. So idea is that so we have to, the free energy minimization is that the accuracy is that actually we have to minimize one side is the accuracy, that is a prediction error. And then the other is the complexity, that's a posterior prior scale divergence have to be minimized. So then, but if we can minimize some of them, then free energy minimized, then your approximate the posterior is going to be a true posterior. So then this one is something like, again, top-down prior things and the likelihood generating, and you have observation, and the bottom-up, the error signal comes, and using this error signal, and then prior is updated to the approximated posterior, and we repeating this one until we got the free energy is minimized. So then I'm going to introduce a recurrent neural network model that is incorporated with this idea. So that's yeah. Okay, so then we developed something called the PV-RNN in 2 years ago. So, and then free energy is actually, it's a little bit complicated term because we have to make things in temporal things. So usually free energy is more written in static things, but we have to extend it in temporal, also learnable way. So, and then again, this is accuracy term plus complexity term. And then we have something called the weighting, something called metaprior. I'm going to discuss this one. This is kind of important things. Later, I'm going to come more. So then the graphical model looks like this for the recurrent neural network. So this is a time. Time goes from here to here. Then we have a probabilistic latent variable of prior and posterior each time step. And then prior is kind of a Gaussian distribution, mean and sigma representation. Then we have and then each time, so this prior is going to change. So, and then posterior we're going to have. So how to obtain posterior those things later I'm going to explain. So anyway, so then and having this posterior, and then we're going to have a deterministic latent variable changing in time again, like this one. And this one is further mapped to the sensation prediction, actually, like a vision perception. So then we have reality comes. Then if there is an error is going to be bottom up and back propagate through time, and the error coming to the posterior. And then we're going to update this posterior and using this error signal for minimizing this reconstruction error, as well as we have to minimize KL divergence between the prior and posterior. So we have two things to do. That is error minimization and prior posterior, that called complexity term, that have to be minimized. So that's the two things have to be done. So, okay, so that is a basic idea of the PV-RNN, variation recurrent neural network. So, and then I'm going to show some kind of first simple experiment running with the probabilistic finite state machine. So that like I consider like simple example, like we consider a simple probabilistic finite state machine. After 1, 0, it generates either 1 or 0, some probability. So then we're gonna, this is going to be generate learning sequence, training sequence exemplar. So that is something like 1, 0, then question state. The question is 1 or 0, but this case is 1. 1, 0, and this goes to 0. It's continue. Then this one is fed into the PV-RNN, and then we're going to change the learning. So that is changing, adapting synaptic weights so as to this kind of sequence pattern can be generated. So, and in this case is importance is that we change the W. That is balancing between complexity term and prediction error part. So, and the changing the W, and then we let the network learn. So then how the W affects W affects the learning results. That is what we're going to look at. So this is a result of the learning. So then this is like a target machine. Then this is in case of the W set relatively large. This is a small one. If we set W relatively large, the first we look at output. This is 1, 0, and 1. This is the question state. 1, 0, 1, 1, 0, 0, 1, 0, 1, something like that. So that actually this is almost representing this one. So this gray part is question state. So 1 or 0, right? So then if we look at the prior latent variable, it's almost saying 0. So, however, if we look at the case of the W set smaller value, And then this sigma goes up whenever it comes to this question state. That makes sense, right? So that is a more noisy. That's why it's going to be this part is stochastic, right? But this is more easy to understand. But this one is what? This one is actually first sigma becomes 0, means deterministic model is self-organized through the learning by setting W is larger. Actually, what we found is that the Lyapunov exponent, some kind of measure of a dynamical system, and it says that positive. So that means that in a pseudo-probabilistic structure is reconstructed by embedded deterministic chaos. So this one is deterministic dynamics. It looks like a probabilistic, but actually deterministic by using initial sensitivity with chaos. This one is generated. This one is completely stochastic because we have this is question state, always sigma goes up. So that kind of different things comes out. So point it, and also, we did some other experiment, and if we set W smaller and larger, but the point is that the best generalization comes between them. So highest generalization. What we can summarize is that by changing this multiplier W, the weighting, then what we see is that if we have kind of fluctuated temporal patterns, so we observe and we want to reconstruct. So then when we change the W larger, it's going to be embedded in deterministic chaos. But if your W is set smaller, so then that's going to be embedded in stochastic dynamics. So there is some kind of continuity between. So that is I wanted to say. And then cognitively, so if we set W larger, means that the top-down things is a small sigma, that is high precision. So estimating that my prediction is very correct. So, and then the small sigma means that it's going to be deterministic dynamics. And the other side, this is going to be low precision because larger sigma probabilistic. And then this one is going to be the more strong top-down, and this one is going to be the very weak top-down things, and it's going to be related to the autism, and then something like that. So, but today I don't talk about that one. Okay, so and the best generalization comes between. So then I'm gonna in order to scale this model. So I introduce again multiple level. Higher level is slowly operated. So, and then lower level is the first, and the time constant tau is a higher level is set larger. And then, so this is neural activation dynamics. So then now I'm going to show you the learning through using multiple level. So that is, we have a kind of top-down activity goes like a prior things. And it goes through time, forward dynamics goes, and it's going to generate prediction, generate an image of sensation. And then when we have an observation like this one, then that is going to be error is computed in the bottom up and also back prop, so retrospective. So it goes, and then we're going to update the posterior as well as synaptic weights. So that's what we're gonna do. So that is a learning process. After the learning, so maybe synaptic weight is fixed, and then we do like actually robot generates the action by sensing the through the by passive sensation. So that real-time operation things, and then how are we gonna do that? So that is now, this is now, let's consider now. Then this is a pass. So then we have a kind of a always, it's every time step what the network gonna do is always to make a kind of a reflecting about the past. So that kind of reconstructing try to reconstruct already observed one. So by the forward computation and top-down things, if you have the error, then always that is going to be an posterior update. So this is something like a process of the agent try to make own context or internal state associated to the past observation of the sequence. So if a new sequence comes, maybe past interpretation of the event is going to be changed. So that is a kind of latent state. Always we have to update. So then once you are now situated, so then you can predict for the future. And this is going to be a kind of a lot of computation because we have to backprop and we do like 100 epochs backprop each sensory motor step each sensory motor step like my humanoid 100 millisteps. So then it's a lot of computation. Then after 100 millisteps, then time shifted. Then again do the same thing. That is always looking at prediction in the future, reflecting the past in terms of post-prediction. So that goes on. Okay, so then I'm going to show you some experiment first. That's that two robot interactive experiments and that kind of synchronized imitative interaction using this model done by my student Nadine and me. Okay, so the synchronized imitative interaction, like these two robots imitate each other, but simultaneously. So, and the idea is that these two robots are pre-trained for the predicting sequences of primitive pattern, which follow the specific probabilistic finite state machine. So this robot learns to generate as well as predict sensation of the first like a primitive pattern. So like doing like this one. Then after 5 times, then 5 cycles, it's going to generate either C, 80% or B, like 20%. So this is the other robot. This robot is going to learn something similar structure of probabilistic finite state machine. This is going to be the A, but after that, it's a bit different. C is 20%, B is 80%. That is different. So that's a conflictive situation we intended to introduce. So then in this experiment, training is repeated with different W value, like I have shown in 1-0 question things. And then after the learning, the two robots interact by generating unintended movement pattern while perceiving the pattern generated by the other. So based on the prediction. So it is going to always predict what's going to be next my movement as well as what will be my next observation. So I'm going to show something more detail about this one. Robot 1, Robot 2, and then it's going to have the prior things, and the prior goes to the both vision. So predicting after 100 millisteps what kind of things I'm going to see, and then also it's going to be predict the proprioception. That is next joint angle fed into the controller and the movement generated through the body kinematics. That body movement can be seen from this robot. So this robot also predicting about the vision and comparing here. And also the joint angle generated and that activated through the controller, and actually then the movement of this one can be seen by this robot. Again, this is a comparison here. If you compare and if there is an error is back propagate in a bottom-up manner and changing the posterior is updated. The same way this robot also updated posterior. So this is it's kind of continuing many sensory motor steps. So then specific question is that what sorts of interaction can emerge under this setting, especially with conflictive situation after A, the either generating B or C is going to be different among two robots. So, and do they always imitate each other like a mirror neuron? Or do they sometimes generate unintended movement by ignoring the other? So that is a question. And then how does W, that weighting parameter, affects the way of didactic induction? So let's look at the robotic experiments for the results. Okay, so then this is two robots, and first This robot set small w. This robot set larger w. So now both are generating A. Then this guy is generating B, and this is actually following. So this robot is more preferring generating B. Now is again the A. So then generating the bit. So you see that this robot is reading, read the first, and this robot is actually following with small w. This is larger w. And then what you see is something like that. This robot is prediction is very strong. So it's stable. So this is actually what I show you is something like this is now and the predicting future. This is the past thing. So I'm saying that this guy is predicting very strongly, and then now I'm gonna do the A. The next is gonna be B or C. No, this is now generating B and then back to the A. So B, A, B. So something like very strongly, but this robot is very weak. So okay. So then this case is that two robots have both W is large. So, okay, so it's now both robots generating A, and this robot generate preferred B, this robot C. So it's kind of conflicting, actually ignoring each other. Both robots generate on future things predicted very stably. And actually they do as they intended, but differently each other. That is the case of the setting W both large. This is the last one in the setting W, both cases very small. So now generating A, the A is okay, have a conflictive state. So it's not really generating, but it looks like C generated, but in not so stable manner. But this case is something more interesting. Sometimes taking kind of more complicated behavior, complicated relation things as we can observe. So, okay, so now we bit showing about the analysis. This is a case of the robot set with a larger W. This is a robot set with smaller W. So this is robot 2, this is robot 1. And then, yeah, this is kind of the output movement in the, you see that completely coherent, mostly coherent. And the important thing is that this is a latent variable of the lower level. And the black one is posterior. Then this green one is prior. There is some kind of the gap. That is because W is set small. That is allowing the divergence between these two. So therefore, it's kind of is a prior and the posterior doesn't agree sometimes. So that is allowance between. But in case W sets 3.4, it's almost identical about prior posterior. So therefore, this is what intended is going to become the reality of a posterior. But this one has some kind of a weakness or elasticity between prior and posterior. So that's kind of difference comes. So then I'm come to the conclusion about this interactive dynamics. So that is, when we set this robot, set W larger, this robot set W larger, it's going to be the prior sigma is very small. It's very precision becomes high. That's why posterior is pulled toward prior. So, however, on the other hand, in case of this weaker W, then prior is going to be more larger sigma. The precision is low. That's why posterior is dragged toward sensation. So that is why this robot is more following sensation. That is the other's movement. And this robot is more like ignoring the other, more toward own intended things. So that's why this robot becomes a leader and this robot becomes a follower. So, okay, so and then we do like this kind of things with the human robot interaction and using force feedback human robot. So that a set, okay, so a set of movement, so in this case, experiment, a set of movement pattern are learned in a meta-stable manner. So different movement pattern is coexist. So, and then human subjects like him is attempts to regenerate each of them through the interaction. So maybe I'm going to show. So now robot generates primitive A, and now he starts to interact. So then his prediction is goes down because he interferes. So then now, so that and the primitive pattern changed to the C. So now again, he is interfering with the robot. So primitive D comes, something like that. So the point is that that we can, the experimenter can feel the intention of a robot in his hand through the active inference, because sometimes robot precision is high, so that the intention is strong. Then you cannot move as you want. So the robot will strongly push you, right? So, but sometimes prior becomes the precision is low, sigma is high, then he's weak. So we can push him to what you want. So something like that's kind of an interaction. It's kind of a physical level interaction, and then that is possible. So it's kind of elasticity is in the physics as well as in the brain of the robot. So that's kind of things we are doing. Okay, so next one is that yeah, using same robot, kind of a goal directed planning by using active inference, so that yeah, so Matsumoto-san, my postdoc, is working on this one. I'd like to show you briefly. So like so planning is also if the robot can predict future, and then planning is possible. So that is so the first is that this is online planning for the future while reflecting the past, something like extending the past framework as the framework I introduced previously. So that is we have a kind of, again, this is the past, now is here, and reflecting the past, the updated posterior. And then once you got straightened, and you can predict. But in this case is that we show the goal image that have to be achieved. So then this is a predicted one. If that goal image, there is a gap between them, then, and because this goal have to be achieved, so then that this gap error is propagating, then the updating the posterior, so as to minimize expected free energy for future. So we're gonna do the both minimizing evidence-free energy for the past by the predict coding, and minimizing expected free energy for the future, so by the active inference. So then if we do, so, but then in real-time application, what we're going to do is that if we do the lot of iteration for every 100 millisecond, then if time comes, and then it's going to update. So it's continue like this one. In that way, we can do the online prediction of future, the online reflection of the past. So that kind of things is possible. So now I'm going to show you some example. So that okay, so this one. So then this one is so now goal is given right here. Okay, so then this is a starting point. So first robot is told that this is the goal. So then this is a starting point. So the object located here. And now prime generation, this is prime generation, this is latent variable. This is now, and then the window, and he achieving the goal. So that is, yeah. And another one is that another goal is shown here. So now goal is here, it's changed to here. and they're located here in the initially the robot generated plan, and then you move. So you see that past window, it's a latent value always changing because some small prediction error exists. So then more like interesting thing is that kind of interfering the robot while robot is generating the plan and action execution. So that is so now robot grasp it and but he is kind of experimentally interacting. So this is now this plan is almost okay, but now it starts to disturb because now it's kind of sensation is going to be different. So therefore, this is something broken, and then now he's making new plans. Now a new plan is generated. So then he's executing this. So that is a defining thing. So that is now he's almost done. So interesting point here is that so he's now almost generating next another plan, or restraighted one. So this is a plan for future, and this is a past sensation. And then interesting point is that the post-prediction. You see something like this part is actually not so much same as this one. It's this kind of that image, fake image. So it's not really exactly of sensation. That is why this appears. That is because in order to make your past interpretation is smoothly connected to the generated future plan. So therefore, past is somehow modulated so as to the accord with the future plan. So that's kind of a past is that is a post-prediction. That's kind of things we see it. So then I come to the final example of robot experiment. Again, this is goal-like planning, but now we're gonna more about the vision. Especially, I'm going to ask the question about how visual attention autonomously generated through learning, and also how the visual working memory, usage of visual working memory, adequate way of using visual working memory can be generated. That is actually using visual working memory, attending is a part of the action, and the active inference framework, through the active inference framework, so we can do it. And then actually we found something very interesting, prefrontal-like like a mechanism emerged. So that's I like to show. So then goal direct planning in robot task is something like this. So this arm robot, the initial block configuration like a red, blue, green things located randomly like here. Then robot is asked, so this is the goal you have to achieve. Visually shown, pixel level vision 64 is given. And the robot have to mentally generate visual proprioceptive pathway of reaching this goal, achieving this goal. So VP image 1. And then maybe then the different initial configuration and different goal, and then you're gonna get another visual imagery, visual perceptive plan, and this one is also again something like that. So this kind of things is done, test things of plan execution after we first train the network. That is a robot experience many way of grasping the object of different color and stacking it in a different location or position or something like that. So we train the network as kind of example trajectory, visual perceptive trajectory in a supervised manner using maybe, I forgot, 300 trajectory, something like that. So then after that, we test like a new configuration of the object things and locate it to the new position, novel position, and then robot can generate it or not, something like that. Okay, so then the conventional approach is something like robotic people kind of build up the planning part, the vision part, and I don't know how much they use visual working memory, but the visual working memory module and the attention module nicely writing the program and the partially training and integrate them. But rather, my approach is something like we consider large-scale network consisting of local network, and then we provide connectivity among local network. That's pre-given. So it's kind of this part of the local network, and the other part is something connected. So then, and then through the learning, and then the local global interaction by minimizing free energy in the learning, and then our model is all differential. That's why so backprop signals go through. So then we look at the emergence of a counting function globally as well as locally. So what kind of function come out in order to achieve the goal? That is in order to minimizing free energy. So then, yeah, so, okay. So then this is the first experiment about it after the enough training, and we do like a planning task. So this is an initial image. Is now, it's kind of after the training using the red, blue, green object, and the initial image given like this one. This is a goal image in a pixel. So, and the first, let's look at what kind of visual perception is a visual imagery, visual prime generated. So this is actually, so you see that it's first green one is put on and the red one is put on, and then actually goal is achieved. That's a visual imagery. So that looks okay. Then now next is a look at visual attention. What kind of visual attention self-organized the learning? So actually the visual attention always goes to these blocks to pick up. So that makes sense. The interesting point is that the working memory, what kind of the image is stored and written and retrieved. So isn't it interesting? So that the first is that the green one comes and the red one comes. So, but you don't see that movement of the robot. And also you don't see the movement of the block. Right? Just a result of the action, and then kind of sub-goal. First green was put on the blue, that state comes, and then next is that then red one, the final goal, red one comes. So that kind of sequence of the state, important state like sub-goal things comes out. That kind of image is generated here. So. And then this finally physically robot achieve in executing the action. So that's okay. So the emergence, what we found is that so this is a goal image and this is a plan generated, for example. So then we often see something like an occlusion like this. See here, the robot camera is actually in front of the robot. So this is robot image. Okay. So then robot cannot see the green one here. The green is here, but because of his body occluded. But this working memory, you see that green here. So the actually then kind of the chunking you see, like okay. First is that I would say that using this one, the concept of object permanency was captured. So that is even though the green one cannot see, but if you don't touch green one, don't move the green one, then the green one is still there. That kind of thing is it looks like developed. So, and the second one is like a chunking by sub-goal structure that's developed. So like this one is one chunk, so, and this one is another chunk. So that is, it doesn't move actually almost, it's same, but when the blue one is come to here, then it's appear here. So as I told you, static sequence, static state, sequence of static state, sub-goal things is, you can see. So the finally this one come to here. So that kind of thing that we didn't expect something like this come. So we thought that the goal can be achieved after the good training, but the more interesting thing is that looking at the internal representation, then something interesting comes out. So, and then And another postdoc comes, and then he said that he wants to brains using not only one visual working memory, but is multiple, at least two. So and one is the parietal area, the other is the prefrontal. And he wants to put the another working memory, and then this architecture that is previous. I have shown, but I haven't explained so much, but it's kind of, this is architecture is kind of a higher level LSTM, and that the executive control recurrent neural network. And maybe this is a ventral pathway and a stack of convolution LSTM taking care about the visual image things. And then this one is about the body movement, and higher level is going to control movement prediction as well as the attention control. And then this is going to be the vision prediction as well as some kind of the mask. So mask is something like an operation like so it's kind of working memory here, visual working memory one, and then masking this part, and then copy this to the another second working memory or something like that. So that's kind of a operation, but everything is differentiable. So the neural network is going to do it. So that's kind of operation and how. So okay. So then the results of new architecture. So I'm going to show.
By the way, this is a 10-minute note.
Okay, thank you. Yeah. Yes, I'm going to finish this. So. Okay, so then this is a kind of a fast. Now green one is pick up. It's always I do the yeah. Okay, so I'm going to show something. Okay, so then it's going to be something like now the green one is picked up. So then, this is a first visual working memory. This is a second visual working memory. So, and now is the robot is approach. This is a visual imagery, the planning things, and then try to pick up green one, and then visual working memory here, the green is gone. Then it's appeared in the second visual working memory, and then it's going to manipulate this one. I can't. It's okay. So manipulating here. So then it's going to be the put on blue one. Now it's put on the blue. So then. Okay, so now appear in here, so the visual working memory 2, and then it is gone from here. It's not gone. Okay, it's now gone. Then now approaching to this orange one is the unseen one. So it's the important point is that this experiment is that the robot is now can deal with unseen new object, which is not used in the learning. So that's green one. But he can also same way generating image about manipulating orange one, and even though it's the first time to see. So and so now grasping it. And this will disappear from here and appear in visual working memory 2. So then, okay, so then this goes like this. It's finally orange one is put on here. So then, yeah, I'm sorry, that is, I don't know why it's always this doesn't come. So then I'm going to explain what's going on. So that is the first green one is approaching, and attending autonomously and grasping it, this one. And then actually this part is masked and copied to the visual working memory too. And then here, this is going to be transformed. So by the prefrontal control. So then this kind of the moving this object image generated. The once this one is put on a blue one, then and green one is now on. So this is a visual working memory too. So then this is something like a prefrontal is doing kind of why is like a parameter providing parameter for the lower level. Lower level have a functionality, develop the functionality of transforming the image like a moving object. But which way to move, that is parameter controlled by the higher level. Other things is that another parameter is masked. So which part is going to be the copy to the another working memory? That's kind of the control the prefrontal is doing. So okay. So then this is also the next step is that this unseen first time see the orange one is approached and then same way is cutting. It's kind of masked this parts to that put on this visual working memory, and the prefrontal is kind of generating image of transforming it. So then finally, this one is going to be put on here. So point is that why the network can deal with this newly seen orange one, that is because context and agnostic information processing is generally developed. The contents, that the image of the colored objects and the function for manipulating them, that the image transformation are separated in this way, in this model. So it's in that way developed. So that is different from the user generated model like convolutional LSTM. So it's going to be the contents to be generated and the way of the manipulating is going to be inseparable. So therefore, it cannot deal with the newly seen object. But in this case, is that whatever things you put in the working memory, regardless of first time see or not, but whatever you put, and this prefrontal is going to manipulate transformation of this, regardless of the contents. That is kind of important. I mean, like a computational, like in masking and cutting and pasting somewhere, and then manipulating them, and then the manipulated one is once back to the copy back to this image, something like that. That's a cut and paste and manipulation. Those things can be done by the continuous neurodynamical system through self-organization. So like we have prefrontal-like executive controls, higher level LSTM called function in the lower level LSTM associated with the control parameter. So, okay, so then I come to the finals. How many minutes I have? Is it 1 minute, 2 minutes?
You have 4 minutes, including discussion. So that's
okay,
not
so
very much.
okay. So then why is the variational recurrent network so essential for modern cognitive minds? The one is that because seamless interaction between the top-down subjective mind and the bottom-up sensory reality in the analog metric space. That is, we have subjective mind, kind of a top-down prediction or intention acting on the environment, and we have an interaction in the environment, and then perceptual reality comes back. Then that's why it's going to bottom up and changing the, then in terms of perception, it's going to be subjective mind change. So we have two sides of the changing inside mind, inside the environment, but how they change depends on this intricate dynamic interaction. So that I discussed already, it's kind of 20 years ago. So, but however, new thing is variational base. That is, we have a kind of a elastic interaction, more elastic interaction, because we have a precision. So if the higher level precision is high, it's going to be more push toward bottom. So the bottom up process is more pushed. So, but on the other hand, if you have the bottom up and the precision is high, then it's the pushback. So it's kind of, this kind of push push and pull kind of interaction, elastic interaction goes on. So when cognitive system has a conflict between what subjectively expected and the environment saying the conflict exists, then just is try to resolve this through the intricate interaction between two sides, maybe taking some time. Then as time goes by, it might be resolved. So that's kind of process is very important. And the Bayesian dynamics, I call it, can provide opportunity for that one. So finally, I say that the phenomenological consciousness, that the non-conflictive situation between top and bottom up with free energy is completely minimized. In that situation, behavior generates kind of a habituated way, familiar way of behavior, familiar environment, no problem. Everything goes automatic, therefore less conscious. However, in conflictive situation, free energy should be minimized, but that's require the effort. Like as I show you, it's kind of a push and pull. That is effortful. That's why it looks like more deliberative, and it goes to more consciousness. Okay, so that's, I don't go this one. So that is the end of my talk today.
Thank you. We have time for one question only. And Martin, is there any more questions at this point? Okay, so Martin, one brief question, please.
I would like to ask, your presentation was very interesting, but quite demanding. So I missed this part, but as I understand, the innovative part, one of the innovative parts of your approach is that you are merging the networks. But how do you achieve these merging networks?
Okay, so in when I talk with the students or postdoc, and I say that don't design so much, but just provide like a boundary condition that is including task condition, and the let's network do it. And then maybe you consider like another constraint, like a time scale difference and also how local network connect to each other. And then just let's look at, so how the network is going to solve the task. And then I ask a student not only look at performance like a neuro IP conference, right? You always ask the performance, how many percent goes up? No, don't look at that one. Rather, something interesting observation internally. Then if you find something interesting, non-trivial, then you look more carefully, and then it might be correlate, something related to the real cognitive neuroscience literature, something like that. So that is a way. So we expect to look more for emergence. I mean, it's not design, and then not to expect too much. So
okay, thank you very much.
Thank you very much.